Hello everyone, thanks for introduction. My name is Pavol Bielik and I'm a PhD student from ETH. And today I would like to tell you more about our project which enables you to find concurrency bugs for Android applications. So to start with, let me tell you what are these concurrency bugs. So for example, we can look at an NPR news application, and what can happen is that the same article is shown twice. In another application, which is a file manager, it can be that it actually shows you a wrong directory, or that the images are shown in the wrong order, and so on and so forth. So what all these applications have in common are two things. So the first one is that all these bugs were successfully found by our tool, reported to developers, and some of them are already fixed. The other one is that all these bugs are caused by subtle behavior which was not intended by the user and not catched by the testing they performed. And all these bugs, since they are concurrency bugs, as you all know, these are very hard to find, and you don't have to go far to look for even big applications such as Google Play, where it can again happen that the same picture is shown twice. Using our approach, we are actually not even only being able to find bugs in applications, but even in the framework itself. And finally, many of the bugs are simply result in crashing of the applications. And again, here you don't have to go far. This is the United Airlines application, which crashed just as I was flying for this conference. So I showed you a bunch of bugs, but what is really the cause of these bugs? So in Android applications, there are event-driven applications, which means that there is not a single main entry to our program, but there are a bunch of callbacks which are invoked by the framework at different times. So for example, if the user starts your application, the framework will call an onCreate method where you initialize the UI and do a bunch of other things. So another thing is that these applications are highly asynchronous. So for example, imagine you want to download some data from the internet. The way you would do it is that you would create a background thread to download this data because you don't want to block the main thread because you want to, for example, show some nice loading animation. When the download is finished, you again post a callback back to the main thread, which shows the results. And when the user decides to stop using your application, again, the framework will invoke another callback, which is in this case called onStop, where you would clean up some resources. So in this simple example, what can go wrong? Well, what can go wrong is that this is not the only execution that can happen. There is another execution where the user, for some reason, decides to close the application before you were able to download all the data from internet. And then depending on what you perform in these two callbacks, for example, if you close the database in the onStop and if you try to insert here, bad things can happen. So what can you do to find these bugs? Well, what can you do is actually you can go online and use our tool, which is available. So let me just show you a quick demo. So you can go to the webpage. It's called eventtracer.org/Android. And you can just go. You can select which Android application you want to analyze. And you can just click Find Traces. And the system automatically finds these concurrency bugs and creates a report for you when you can go and fix them. So with this in mind, how can we actually build this tool? So what are the key ingredients? So here in our tool, we perform several steps. So the first one is that, as you have shown, we take your application, we have an instrumented system, and we run the application. As we run the application, this collects a single trace of one application run. So in this case, for example, imagine this application run correctly, and these were executed in this order. But as I have shown you, this is not the only possible execution. So what we would like to do is we would like to extrapolate from the single trace to a set of traces which define all the possible behaviors that your application could have done. So here, for example, it is guaranteed by the framework that this onCreate is before you start downloading the data. So we add an edge here. Similarly, there is an edge between these two events, but there is, for example, no edge between these two. And in the next step, what we do is that we look at all the events which are unordered and which conflict. And by conflict, we mean that they access operations, for example, inserting and closing the database that that can be harmful. And finally, it turns out that if you just do this naively and report all such conflicts, there are just too many of them in order for the tool to be usable. So we perform some filtering and grouping to reduce the amount of burden for the developer. So let me now go through each of these steps in more detail. So first, the question is, we want to have an instrumentation, but what does this instrumentation actually track? So the first thing is we want to track all the relevant applications that capture the essential features of event-driven applications. So for example, if I have these callbacks, I probably want to track when they begin and when they end. Similarly, if I have the standard operations using threads, such as forking a thread or joining a thread, this is again an operation that I want to capture in my trace. Similarly, if the user uses some API provided by the framework, such as this called post-delayed, which schedules an event to be executed after 100 milliseconds, I again want to capture it in my trace. And what we did is that we defined 11 operations, and we provided a mapping for all the APIs in the framework to our 11 operations on which we then can perform the analysis. In addition to capturing these essential operations, we also capture the memory locations, which are used to detect the conflicts. So here, since the Java programs are written in since Android programs are written in the Java, these are the standard object and class fields. But additionally, we support so-called high-level operations. So here, for example, imagine you want to do the insert into the database. You are not really interested in the low-level writes into the database connection, but you are interested in the fact that you, for example, wrote in the table users to a row with ID 2. And this is something we can support. And the important thing here is that this instrumentation has to be actually done for both the application and the framework. And the reason here is that if you don't do this, you are going to miss harmful bugs. So you really need to instrument both. But as you can imagine, instrumenting every read and every write of a variable is a very expensive operation. And what we have been able to do is to have this instrumentation with overhead only 3x. What in practice, this means that if you run it on a real device, you can barely see the difference. In the next step, our goal is to take the trace and introduce these ordering edges between them. One way to do it is that in the simple models, such as this fork join model, it's very easy to do because you have these very simple operations, such as fork join, wait, modify, and so on. And the rules are very simple. So for example, you would say, if I fork a thread with a given TID, and I see the first operation in this thread, these two are ordered, right? This is very simple. Unfortunately, we cannot apply this directly to Android because in addition to the standard threads, there is a rich event-based model, which includes things like message queues, binders, executors, and so on, which enables you to, for example, say, I want to post the message with a delay, or at the given time, or at the front of the queue, or only if the queue doesn't have anything to do at the moment, and so on. And what we did in our work is that we tried to formalize these operations and what are the guarantees when you can order them, and then when you do this, you end up with rules like this, which are really complicated. And they are complicated because your definition wants to be very precise. And it's not important to actually read this. And you can find it in the paper, so there is a bunch of them. But really the key point to take away here is that this enables us to have a thorough and precise happens before model for Android, which defines the ordering guaranteed by the framework, on which you can build different analysis systems. So in our case, we decided to find concurrency bugs, but you can use it for other purposes as well. So with this, our goal is we want to, for example, take the main thread in an application, and we want to add all the orderings guaranteed by the framework. But it turns out that you cannot just look on the main thread in installation. You need to also look at other threads, which might dispatch events which are created by the user. And you also need to look at the standard threads which are created by the user, which also can affect and add some edges in these graphs. And it's, again, not enough to look at the application, but you have to look at all the framework threads that the user might not even be aware of. And in fact, again, it's not enough to look only on the application, but you have to look on the whole system, because there can be intra-process communication between either two applications or application and some system service, and you want to capture all these causalities. And so what you want to do is you essentially have a graph of the whole system, and you want to go take the happens before rules we define and add an edges. And since this is, you have to do this for the whole system, it's crucial that your algorithm for building these graphs is very efficient. And in our work, we designed such an algorithm, and there are several key ingredients for make it scalable. And some of them are, for example, in many places, you want to have a fast connectivity query. So for example, I want to know whether these two nodes are connected, and I want to know it in a much more efficient way than just doing a depth-first search, for example, from this one node backwards. Another thing you want to do is that here, these are all the happens before rules we have, and suppose you have a new node here, and you want to figure out what are the edges you should add. So what you do, you go through the rules, and you try. Can I add some nodes from this rule? No. Can I add some nodes from this rule? No. And you go, and you find out that this rule actually adds an edge here. But what happens is that you already evaluated all these rules before, and now since there is a new edge in the graph, you have to go and you have to re-evaluate them again in order to be sure that you don't miss any edges. But of course, this is inefficient, and what we did in our work was we actually defined the rules and the order in which you evaluate it in such a way that a single pass is sufficient in order to add all the edges in your graphs. So once we do this, we have a scalable algorithm for building this rich happens before graphs for the whole Android systems. And once we have it, what we want to do is we want to find these conflicts. And here, so the input is the happens before graph and the memory locations. And here it turns out that we can simply reuse the state-of-the-art race detectors. And what we get out of them are two kinds of conflicts. So the first one is the standard atomicity violation conflicts. So these happens between two different threads, which are not properly locked. And the other one is ordering violations, where you have a single thread, which is, for example, the main thread, and you have just two operations which can happen in different orders, and depending on which order they happen, it can have a different outcome. Now, the problem is that if you just go and return all these conflicts to the user, there is simply too many of them. So for example, if you look at an average applications, there will be like 1,300, which is clearly not something which is very usable for the developer, so you want to do something about it. And the reason why there is too many of them is because many of them are actually harmless. And they're harmless because if you look at, these are the races which are due to ordering violations. So for example, if I look at the main thread of the application and I have two events which both increment a variable, I don't care in which order they increment the variable because the result will be still the same, right? Another thing which can happen is that these can actually commute. Again, I have two events, and then just simply insert something into a hash map at the different locations, which is, again, fine. Or it can actually be that the user tried to actively synchronize these two events to enforce order. But again, you will see a low-level data race on the synchronization variables. So what we did is that we tried to filter as many as we can, and as a result, we can actually reduce the number of conflicts we report to the user by 2 orders of magnitude. So from 1,300 to something like 13. So how well does the system work in practice? So if you look at the scalability, we had a look at many of the applications, including big ones like Facebook, Dropbox, and Twitter. And what we did is we took the applications and we ran them for 10 minutes. And by running them, I mean we were actively using the application, trying to explore as much as possible. So in these applications, if you look at the main thread, there were about 28,000 events executed only on this single thread. And in the whole system, there were almost 600,000 operations. So the graph had 600,000 nodes. And for this, the end-to-end analysis took between 70 to 130 seconds, which is very good. If you look at the actual usability of our tool, we looked at 8 applications. We downloaded from the Google Store, which also had the source code available for us to have a look and to confirm all the bugs that we reported. And here, if we again look at the main application thread, we can see that 25% of the reports were actually harmful, which we reported to the user. And there is still some room to improve the filters we created. The main reason for these harmless bugs here is because we really have to instrument both the application and the framework. And due to the instrumentation of the framework, there are many corner cases which are difficult to find. And of course, in addition to the main application thread, we also reported the standard concurrency atomicity violations between different threads. So I would like to mention also some related work, in particular the work by KAPHA and Droid Racer. And there are several major differences in our approach. So the first one is the scalability. So as I showed you, we are able to analyze interactions of up to 10 minutes in very reasonable time, and we can do even more, whereas the prior work, they were exploring traces from 10 to 30 seconds, and even though they were so small, it took them from 30 minutes to 1 day. Another major difference is the precision of the happens before model we built, where here we cover, our model is much more precise, handling things like message removal, barriers, IPC communication, and so on. And this is important because this, again, enables you to do more precise analysis. And finally, in terms of coverage and usability, if you look at KAPHA, they consider only null pointer dereferences. This is because they want to avoid all these, they want to produce amount of reports which is usable for the user. And here, if it's only 9 pointer dereference, this is it's essentially always a harmful bug, right? Because it will crash your applications. But what it means is that they miss other bugs. So for example, all the bugs are showed you in the beginning. They are not capable of discovering them. In the Droid Racer, they try to instrument also the application, which improves the bug coverage, but they don't do any filtering, and then they still miss bugs because they don't instrument the framework. In our work, we essentially cover everything before, plus also the framework, which gives much more stress to the scalability and efficiency of the analysis because the framework is such huge. Instead of instrumenting a single application, you have to instrument 10 or 50 of them on the whole system. So to conclude, we created a first scalable system for finding concurrency bugs on the Android. The main challenges were building precise happens before model, which in our case we used it for finding bugs, but it can be used for other purposes. And we built such bunch of filtering and grouping techniques that enables the tool to be actually usable for real applications and developers. Thank you.